Okay, so it is my pleasure to introduce today's speaker, Hugh Thomas, who's going to give us a talk titled Representation Theory of Lattices and Rowmotion. So thank you very much.
Hey, well, thank you. Thank you very much to the organizers for the chance to speak here. Próxima vez, tal vez pueda dar mi charla en español, pero esta vez no. So maybe one day. Anyway, so yeah, let me. So the things I'm going to be. If I got that right. Yes. Okay. Right. So I'm going to be in this talk mainly drawing on some work I've been involved in, and also a paper by Iyama and Marczinzik, which kind of got the ball rolling on this story. It's from a few years ago from Advances in Math, yeah. Okay. So. What's the overall goal of what I do, really, as somebody kind of at the combinatorial end of representation theory? And I guess one of the things that I think of as what I do is I want to investigate maps that look like this, right? So things that turn algebra into combinatorics. And the kind of map that I mean are things like, take the Gabriel quiver, or the Auslander Reiten quiver, or the tau tilting fan. So those are all examples of the kinds of things that I mean. And so the interest in this, or the reason that the way I think about what I'm doing is that algebra is hard and combinatorics is easy. And so we want to, in trying to understand the hard algebra, we turn it into easy combinatorics. And so this involves doing some work to kind of extract from the algebra to kind of like let the algebra blossom out into some beautiful combinatorics. And by and large, I want to think of the combinatorics as something that we understand well. So I typically want the combinatorics to be something finite. In the sense that, if an infinite graph is combinatorial, but it's hard to say that it's something that we understand really well. It also is something we can't usually implement easily in a computer, and that's another thing that's advantageous about having combinatorics, is it's something we can work with explicitly in a computer. So for thinking about the Auslander Reiten quiver or the tau tilting fan, we need some kind of hypothesis on, well, I guess, okay, so honestly, I'm always thinking about finite dimensional algebras, though one could, of course, think more generally. But you even need further hypotheses if you want the Auslander Reiten quiver or the tau tilting fan to be something that's finite. So let's say we don't want to put such hypotheses, but we'd still like to find interesting combinatorics. Well, certainly the Gabriel quiver is an example of like nice combinatorics that we get out just starting from thinking about the projective modules. But so what could we do that's a little bit more than the projective modules? Well, we could take the projective modules and the injective modules. And then what might we do with that? Well, a thing we can think about is injective co-resolution of the projective modules and dually projective resolutions of injective modules. And so that is like a finite amount of information, and it's something that's, it's going to be well defined for any finite dimensional algebra. And so it's something that we could hope to, extract some interesting combinatorics from. And I'm going to tell you kind of a story about that. today. So in particular, I'm going to be talking about Auslander regularity, though not exclusively. Is the audio okay? Is this
Yeah.
great? Okay, thank you. So for a finite dimensional algebra, it's called Auslander regular. If it's a finite global dimension and when we think of taking an injective co-resolution, then we look at the projective dimension of I, it should be less than or equal to I. So, I mean, to me, that was a pretty funny looking definition when René Marczinzik told me about it to the first time. It didn't strike me as like an obviously like it's not an intuitively obvious, obviously interesting thing. Where does it come from? Well, it comes from work of Auslander. And so the point is that in fact, for a commutative Noetherian local ring, so kind of a different setting. But anyway, so A is a commutative, A is very briefly a commutative Noetherian local ring. The above condition of Auslander regularity is equivalent to the usual notion of regularity for local rings. So that's where this kind of funny looking definition comes from. It comes from commutative ring theory, which people who know Auslander's work know that, you know, he came actually into finite dimensional algebras from commutative algebra, and so this definition he brought with him. So I'm going to be interested today the algebra being the path algebra, or sorry, the incidence algebra of a lattice. So L, a lattice. I should say L, a finite lattice. So in other words, L is a poset with well-defined meet operation. So this is the meet is the greatest lower bound of x and y, and it's denoted x wedge y. Okay, so for any pair of elements x and y in the lattice, there's a greatest, the unique biggest thing that's less than both of them, and dually a well-defined join, which is a least upper bound denoted x v y. Okay. And so once we have a lattice, K is just going to be a field. It doesn't really matter what field for my purposes. And then we're going to write KL, the incidence algebra, is just, we take the Hasse diagram of the lattice oriented upwards and impose relations so all paths x to y for x less than y are equal. Okay, so that, for example, if we had this 5-element lattice, where what I've drawn is the Hasse diagram, which means that I've drawn the 5 elements and I've drawn the cover relations, which are the pairs of elements where one is less than the other, and there's no other element between those pairs. And so this is enough information to recover the lattice. And so from this lattice, we're going to think about orienting the edges so that the cover relations point upwards. So now we have a quiver, and then we're going to impose a relation that says that paths, different paths from between the same pair of elements will be equal. So that, like, for example, there'd be the relation that says that that path would be equal to that path because they're just two different ways to go from here to here. So then that defines the incidence algebra, and we can then also talk about, you know, representations of the lattice, which are just modules over this incidence algebra. So there is a notion of representation theory of lattices or posets that was studied like 50 years ago, where there's other conditions. We're not doing that. We're just doing modules over incidence algebras. That's all I'm doing. And the interesting thing is that there's interplay between the combinatorics of lattices and the representation theory. So let me start to explain that by spending a little time with the work of Osamu and Rene on distributive lattices. So first of all, I should explain what a distributive lattice is. So if R is any poset, then Y, a subset of R, is called an order ideal if whenever we have little y in Y and X less than or equal to Y, then X is also in Y. Okay. And then, so given R a poset, we let J of R be the set of order ideals. And we can view it as a poset by ordering them by inclusion. And it turns out this is a lattice. It's fairly easy to see that that's a lattice. And then a finite lattice is distributive if it's isomorphic to J of R for some finite poset R. So there's another definition of distributive. You can also define it by saying that the join operation distributes over the meet operation, and you can also define it by saying that the meet operation distributes over the join operation. So it's kind of different from the way things work in, like, you know, the kinds of algebras we normally deal with, where, you know, distributivity only works one way between addition and multiplication. So one way it works, you know, I forget which way you say it, like, you know, multiplication distributes over addition or distribute, anyway, which way, whether you say it one way around or the other way around, but only one of them works, right? And the funny thing is that in lattices, they actually imply each other. But yeah, so let me just do a little example so we see what I'm talking about. So that if we had, for example, this as my poset. So what are the order ideals of this poset? Well, I could take the empty order ideal with nothing in the poset. I could take just the leftmost element, right? That's an order ideal. I could take just the rightmost element. That's an order ideal. I could take the two bottom elements. That's an order ideal. Or I could take all three elements. So those are the order ideals. I'm not allowed to take the top element, but not take the left element, for example. This is not an order ideal. So these five are the five order ideals, and if I order them by inclusion, then I get this little lattice that I already had drawn a picture of the Hasse diagram of before. Okay. So it's a really nice result of Iyama and Marczinzik. For L, a finite lattice, the incidence algebra is Auslander regular if and only if L is distributive. So I'm not really going to give the proof, but just to give you an idea of the proof, of one direction of the proof, the point is that using this idea that if you have a distributive lattice, you can view it as a lattice of order ideals in a certain poset, then you can give an explicit description of the injective co-resolution of the indecomposable projectives. So that's what Iyama and Marczinzik do. Well, so there's a theorem due to Auslander and Reiten that says that for an Auslander regular algebra A, there's a bijection, the Auslander Reiten bijection, from the indecomposable projectives to the indecomposable injectives. And basically the way to go from the indecomposable projective to the indecomposable injective is you take the last term in the injective co-resolution. And to go backwards, you take the last term in the projective resolution. And so it's part of the theorem that this last term actually is indecomposable. So let's look at an example. So here we are with an example. I'm using this same distributive lattice that I've been talking about. You know, this lattice over here, and I filled in the description as order ideals in the little 3-element poset. So don't worry about everything on the page so far. We'll be coming back to this page repeatedly. But let's look at, so here what we have, oh, I need to get this out of the way. Oh, I can put it over here because we don't need this part yet. So what we have here are the projective modules. And notice, let me just say, just in case this is unfamiliar to people, because of the definition of the incidence algebra that says that all the paths from X to Y are equal, that means that the projective modules are just going to be one-dimensional where they are supported. So I've just drawn them by filling in red where they're one-dimensional, so that, you know, this guy here is the projective module corresponding to this vertex. This is the projective module corresponding to this vertex, and so on. Actually, I think I'm going to try to fill that in here. So this is the projective module corresponding to this vertex. This is the projective module corresponding to this vertex, this vertex, this vertex, and this vertex. Okay. And then what we have in each of these cases is the injective co-resolution. And what we look at when we look at the final term of the injective co-resolution, so we see that sometimes some of the terms are not indecomposable, but when we look at the final terms, we're seeing injectives, and what we're seeing a single indecomposable injectives, right? That's what I wanted to emphasize. And which indecomposable injective? Well, we get a different indecomposable injective in each case. So this is a manifestation of that Auslander Reiten property that I said, namely that this is a bijection from the indecomposable projectives to the indecomposable injectives, where what I'm saying is this indecomposable projective is sent to this indecomposable injective. This indecomposable projective is sent to this indecomposable injective. And since both the projectives, indecomposable projectives, and the indecomposable injectives are indexed by the elements of the lattice, we can really think of the Auslander Reiten bijection. Why is it being fussy? Oh, okay, there we are. We can really think of the Auslander Reiten bijection as a permutation of the elements of the lattice. So so in each case, we're asking the final term in the indecomposable, the final term in the co-resolution of the projective corresponding to this guy. It's the injective corresponding to who? Well, we look and we see, oh, it's the injective corresponding to this guy. So we send this guy to here. To see where this guy goes, we look at the projective. We ask, what's the final guy in the resolution? It's him. And so this projective, so this guy is sent here. So the Auslander Reiten bijection is defining a permutation of the elements of the lattice. And let me just make a copy of this, because I'm going to copy it onto the next page, and then we're going to try to describe how that works. Let me, yeah, okay. So we're going to try to give a description which basically follows immediately from Iyama and Marczinzik. But let me also, before I do that, let me just look at an example of a non-distributive lattice, so we can just see the process not working in the same way when we start with a non-distributive lattice. So here we have this this lattice with 5 elements. It's not distributive because distributive lattices are always graded. They come in layers. This one doesn't come in layers, so definitely not a distributive lattice. And what we see is that, this indecomposable projective, the last term in its injective co-resolution is this guy, but this indecomposable projective also has that same guy as the last term. So we're not getting a permutation any longer. So this isn't working because in some sense, this is not Auslander regular. And the reason it's not Auslander regular, according to Iyama and Marczinzik, is because it's not distributive. Okay. So how could we describe this bijection, this Auslander Reiten bijection? Okay, so we need a little bit of lattice theory. I mean, I guess unsurprisingly, I want to describe this as permutation of the elements of the lattice. I need some lattice theory. So for X, an element of the lattice, pop down of X is X meet the meet of all the elements Y, where Y is just below X. And so that's kind of an interesting operation. And it seems like it might be a little bit related, because if you start with, well, that's not what I meant to do. If you start with, well, that's not what I meant to do either. If you start with this guy and you take the meet of everybody that's just below it, well, the only guy just below it is him. So if you take the meet of these two, you just get this. And so the pop down of this guy is here. If you start with this guy, and you look at the guys who are just below it, it's this one and this one. If you take the meat of those two and this, well, that gets you down to there. And in both those cases, that was exactly the same thing as the Auslander Reiten bijection. But that, I mean, that stops working. The Auslander Reiten bijection sends this guy all the way back up to here, but the pop down of this is just this same thing itself. But so somehow we might nonetheless have an impression that the pop down is related. And in fact, it is. So the row motion of x is defined to be the maximum among all y's such that y meet x equals pop down of x. So that's a slightly funny definition, but anyway, there it is. It turns out that for distributive lattices, we can just see that there is thinking about distributive lattice in terms of order ideals. It's kind of you know, you can unpack this definition very explicitly as, you know, oh, I have an order ideal and I send it to this other order ideal. It's quite easy to describe. I'm not going to give an explicit description, but it is actually easy to describe more explicitly. And this operation has been studied very intensively in dynamical algebraic combinatorics, which is a sort of a recent area, largely devoted to studying this operation. Actually, that's not completely true, but somehow the people in dynamical algebraic combinatorics got really interested in this operation and have been studying it for the past 15 years. And without ever like giving a totally convincing explanation of where it comes from. They're just like, wow, this operation is really cool. And so to me, it's really interesting to see here, it really, oh, I didn't make the statement that I need to make this, okay, sorry. So let me make the proposition that says why I did all this before I am being so congratulatory. So the Auslander Reiten bijection sends P of X to which indecomposable projective? The indecomposable projective corresponding to the row motion of X. So this is more or less immediate from the description of the co-resolution by Iyama and Marczinzik. They don't specifically mention this. They're actually thinking about the same Auslander Reiten bijection, but they're thinking about it in terms of a different bijection that Iyama introduced called the grade bijection. It turns out they're the same, but I actually prefer the Auslander Reiten bijection, and so that's why I'm presenting this in terms of the Auslander Reiten bijection. But the way that Osamu and Osamu and Rene talk about it in their paper is in terms of something called the grade bijection. But anyway, the point is, once you understand what the co-resolutions look like, you can say what the last term is, and that allows you to describe the Auslander Reiten bijection. And it's just row motion. And so this row motion operation, which people in combinatorics have been studying, turns out to really have like a natural significance in representation theory. Also, so in general, this row motion, you know, I mean, you can define it for any distributive lattice, and it's some permutation. And in general, it's just some crazy permutation, and it can have like catastrophically high order. But sometimes row has surprisingly low order. And this seems to be related to the incidence algebra, or the representations of the incidence algebra being fractionally Calabi-Yau. And I'm not going to say more about that. I don't actually have anything intelligent to say about that, but there are cases where we know that these algebras are fractionally Calabi-Yau, And though in those cases, it also happens that the rowmotion has low order. And there's other cases where rowmotion is known to have low order, and it's conjectured that the category is fractionally Calabi-Yau. I mean, it's not that easy to show that the category of representations is fractionally Calabi-Yau. This is some statement that some multiple of, if you look at the derived category, some multiple of the shift functor is equivalent to some some multiple of the shift functor is equivalent to some multiple of the Auslander Reiten translation, or the Serre functor, whatever, however you like to say it. But yeah, so anyway, so it's in general hard to get a handle on that, but there seems to be some connection between this fractionally Calabi-Yau property and rowmotion being low order, and that's something that's like quite mysterious still. Okay, well, so let me keep moving along and tell you something that's a bit new. So let's talk about Coxeter matrices. So for L a lattice, we're going to fix a linear extension. So what that means is, if I have my lattice, the one that I've been talking about, I'm going to number the elements from bottom to top. And obviously, I have some choice about how I do that, well, unless the lattice is a chain. So typically, I have some choice about how to do that. But I don't want to just number them in a completely arbitrary way. I want to number them really, from bottom to top. That's what linear extension means. Once I've done that, then I can think about the Coxeter matrix. By definition, the Coxeter matrix phi is just going to send the dimension vector of the indecomposable projective pi to the negative of the dimension vector of the indecomposable injective. And since I want to think about phi as like an explicit matrix, and so that's why I chose an order so that I want to think of phi as an n by n matrix, and so that's why I needed to have an order so that my dimension vectors are actually in Zn. It turns out that the ijth entry of phi is the signed multiplicity of ij in the injective co-resolution of pi. So that's relatively easy to check. Well, it's very easy to check. So in my work with Renee and Vicky, we showed that for L a lattice.
Sorry, Hugh.
Yeah.
This observation that you make, this remark, is for any algebra or for algebras coming from distributive lattices?
No. That's it's I think it's just any algebra.
All right.
Yeah, I mean, basically, it's it's really just, well, okay. So I guess I need finite global dimension because, or I need at least that these injective resolutions are finite, so that I have an actual change of basis.
Right.
But then, yeah. So this is really just reflecting so this sign multiplicity thing is really just reflecting the fact that this is telling you how to express the dimension vector. I mean, a projective resolution, an injective co-resolution of a projective, in particular, gives you a way to express the dimension vector of the projective as a linear combination of the dimension vectors of the injectives.
Right.
That's what's going on.
Right. Yeah. And this, sorry, and the sign comes from -1 to the I times j or something like this. Yeah.
It's no, it's not that. No, it's minus. The sign is reflecting the position in the resolution.
All right. Yeah. Of course. Yeah. Of course.
Yeah.
Yeah. For the it's like for the Grothendieck group. Yeah. Of course,
Yes. Exactly. Yes.
It's checked. Yeah. Okay.
Yeah. That's what's up with that. Yeah. Okay. So for a lattice, the following are equivalent. So one, KL is Auslander regular. And by the work of Iyama and Marczinzik, that's the same thing as L is distributive. And the novelty is following. The Coxeter matrix lives in W times B, where W is a permutation in W is a permutation thought of as an element of GLN. So W is a permutation matrix, and B is upper triangular. So, so this is saying that phi, the Coxeter matrix, is a permutation times an upper triangular matrix. And what this boils down to is the leftmost non-zero entries of the rows of phi are all in different columns. And in this case, the permutation W is just the inverse of row motion. So this one of the two implications is pretty easy from the work of Iyama and Marczinzik. So in the case where you have a distributive lattice, it's pretty easy to see what's going on. Let's just look at the example again. So here now is the Coxeter matrix, and so you can check that it satisfies this property if you like. And the ith row, so this is the other property that I mentioned, the ith row records the sign multiplicity of the indecomposable injectives in the co-resolution of the ith projective. And then here I've written it as a permutation times an upper triangular matrix. And what that's doing in less like fancy language is I'm just reordering the rows so that now it's upper triangular. And I can do that because the initial entries of the rows are in different columns, so that I'm going to put at the top the row that goes all the way to the left. And I'm going to put the row that goes one less, that goes all but one step to the left. And then I'm going to, so I'm going to order them like this, and that's it. And reordering the rows is exactly what's accomplished by multiplying by a permutation matrix. So that's this is not really very magical, except insofar as all of linear algebra is kind of magical. And so then the Auslander Reiten bijection is just the inverse of row motion. Yeah, so and the permutation matrix gives us is the inverse of the row motion. Yeah, okay. Oh, right, and I mean, why are the thing that we were noticing that was the leftmost terms are each time in a different column. Well, that's because the leftmost terms are actually the final terms in the co-resolutions, and so that's going back to the Auslander Reiten result, that the final term and the co-resolution are different, and they're giving us a bijection, and it's this all part of the same bijection. So it's really part of the same story. It's just it's a different way of telling the story to say that, oh, we can factorize the Coxeter matrix as a permutation times an upper triangular. But kind of interestingly, I think, that turns out equivalent. And, you know, so you don't need to recognize or to test that something is a distributive lattice, you don't have to like do a lot of representation theory. You can actually write down the Coxeter matrix and then ask like a very linear algebraic, very simple linear algebraic question about the Coxeter matrix to see whether the thing is distributive or not. Sorry, was there a question? Oh, okay. I thought I heard a question. All right, great. So yeah, so that's yeah. So this is one of the main results in my paper with Vicky and Renee. All right. Oh, and let's look at the non-example as well. So again, you know, because we have this phenomenon that the last term in both of these co-resolutions is the same, that winds up translating into the fact that the leftmost, there are two different rows whose leftmost term is in the same column. And so there's no way that we could reorder the rows to make this be an upper triangular matrix. So you can see that the failure of Auslander regularity is already kind of manifest in this very, very explicit way as a statement about the Coxeter matrix, you know, in this very, very explicit statement about the Coxeter matrix. Oh, I should have said in both these examples, I needed to choose a linear extension, and that's what I did over here. I numbered the elements to have my linear extension, and here I know like this. It turns out, I mean, the choice of linear extension isn't important, but you have to make one to be able to write down the matrix. Okay, so yeah, okay, so great. So this is kind of we think this is kind of cool. Oh no, I'm sorry, my laptop is going to run out of battery. Am I going to need? Well, maybe that's not. It's not a catastrophe because I'm actually not using it for either the sound or the all I'm using it for is the camera. Maybe I'll just plug it in. And not look at it right now. Sorry. So okay.
Yeah. In the meantime, can I ask a question?
Yeah, sure.
So in this non-example, I mean, this is, well, maybe you can answer this at the end, right? But there is a way to, there is a natural quotient of this that is actually distributive, which is merging 2 and 3.
Yeah, that's true. That's
something that you could do, or is something that can... Could you restrict to those and have something interesting?
Yeah, that's an interesting idea. That is an interesting idea. And I mean, so restricting like that, I mean, I guess the natural thing to think about would be, you know, to think about the subcategory, where you insist that this arrow is actually an isomorphism, because
right.
So that would then be, that subcategory would be isomorphic to the representations of just the 4-element lattice like that, and which is distributive. Yeah, that's really interesting. We haven't thought about that. yeah, we have not thought about that.
All right.
Okay, so let me keep going. Okay, so so more generally, how could you proceed? We'd like to, let's say we like this idea that we're getting a permutation from a lattice. How else could you do that? Well, it turns out there's a very general idea which is applicable here, which is GLN, like the invertible n by n matrices, can be written as a disjoint union over W in Sn of upper triangular matrix times W times upper triangular matrix. So this is called the Bruhat decomposition. And so in particular, any matrix in GLN has a well-defined, permutation associated to it, namely, which of these cells does it belong to? And so we can ask that for the Coxeter matrix. In general, that might not be, I mean, so that's perfectly well defined as such, but in general, it depends on the choice of ordering of the simples, because when you permute the rows and columns, that will change the choice of W. In the distributive lattice case, though, what we just saw is that it doesn't depend. If you think about, so for L distributive, the permutation W corresponding to the Coxeter matrix is just row inverse, independent of how you chose your, well, provided you chose a linear extension. Which seems like a reasonable thing to ask for. So, all right, so let me keep going. So we'd now like to talk about,
yeah, about the row motion. So in this case, then for sort of each layer, so the orbits of a given vertex in your lattice would have all the other vertices that are in the same layer as that one, right? This is it.
No, I don't think
Not
so.
necessarily.
I mean, no. Okay. I mean, I guess in this particular example, I mean, we have. I guess, okay, in this example, that's true, but I don't think there's any. I don't think that's true in general. In general, it's hard to understand the orbits. Like for like Boolean lattices, for example, like which we think of as like lattices that we like. If you think about the orbits, there's their sizes are chaotic. They're hard to understand.
All right. Okay.
In general, so we'd like to extend this story beyond the distributive lattice case, and it turns out that there's an interesting class of lattices for which it's possible to do that. So these are the semidistributive lattices. So L is called semidistributive if, and so this is also like a kind of weird technical condition, but it turns out to be interesting. So if you have x meet y equals x meet z, then you also have x meet y equals x meet y join z. Okay. And you also have the dual condition as well. So it's kind of a weird technical condition. Distributive implies semidistributive. So it does generalize distributivity. And lattice torsion classes are hardly ever distributive, but they were always semi-distributive. So there are interesting lattices that are semi-distributive. So it's a result from the second one of the papers that I was involved in that I mentioned at the beginning, that if L is semi-distributive, then for any linear extension pi, if I take the Coxeter matrix with respect to pi, so I can define a permutation by saying that it's in the Bruja cell corresponding to W pi, then W pi doesn't depend on pi. And further, how can we characterize it? Well, let me copy some description that I gave before. So this rowmotion definition, this maximal element such that y meet x equals pop down of x, this is well defined. It's not well defined for a general lattice, but it's well defined for semi-distributive lattices. And just by the definition of semi-distributivity, it turns out that this property, that knowing that x meet y equals x meet z implies that x meet y also equals x meet y join z, that says that you can think about all the elements y that have the same meet with x, and you can take their join, and that will also have the same meet with x, and therefore there's a maximum one. The join of all of them is itself an element of this set, and therefore there's a maximum element. So this rowmotion is well defined for semi-distributive lattices. So this definition was given by Defant and Williams, and they showed it agrees with a previous definition. Which was given by Barnard. So anyway, so there's a well-defined notion of rowmotion also in this setting, and so it's very natural to ask, how is that related? And it's related exactly the way you would like. So it's a proposition from my paper with Defant and Zhang and a whole bunch of other people, that for L semi-distributive, we have this permutation that you get from the Coxeter matrix is the inverse of rowmotion using this definition of rowmotion. Further, or let me not further, but also, if for all linear extensions pi, W pi is the same, let me say W pi is independent of the choice of pi, then in fact there's a converse. L actually is semi-distributive. So semi-distributivity turns out to be exactly the right condition to have this sort of well-defined permutation that you can extract from the Coxeter matrix. If it is semi-distributive, then there is a well-defined permutation. If it's not semi-distributive, it really depends on the choice of how you order the simples, and that's sort of unsatisfying. it suggests that the construction is kind of artificial. Here, there's really, independent of the choice of ordering, there's a unique, well-defined thing. So this is all kind of, this is kind of appealing to me. I mean, it says, oh, there's some nice combinatorics for semidistributive lattices that generalizes the story for distributive lattices, and that relates the Coxeter matrix to rowmotion. So that's all well and good. It doesn't have, well, or what I said so far doesn't have a lot of. I mean, I haven't said a lot representation theoretically. When am I supposed to stop?
You have like 15, 20 minutes more.
Okay, super. So I'm going to stop pretty soon, I think. But I do want to. So I do have like a final section, and then we can have questions. So the final thing I'm going to talk about is recent work that I've been discussing. It's not written up yet, but so I've been discussing it with Iyama and Marczinzik and Marcus Kleinau and Vicky Klaas. And so this is this notion which we're calling Coxeter witnesses. So the idea is the following. Say you had a collection of modules x sub I for I in L, and satisfying following conditions that xi modulo its radical is si, and the smallest element and there exists a smallest element w of I such that the injective I sub wi appears in the co-resolution of x sub I, and this w is supposed to be a permutation. So for each of these xi's, there's some different smallest injective that appears in it. Well, in this case, for pi a linear extension, phi can be written as upper triangular matrix times W inverse times upper triangular matrix, and W inverse times the second upper triangular matrix encodes the injective co-resolutions of the xi. So the idea is that in the distributive lattice case, we were looking at the injective co-resolutions of the projectives, and that's what's encoded in the Coxeter matrix. But it turns out that by allowing ourselves, and in that case, we were looking at matrices that could just be written like this, without any first upper triangular part. But now what we're doing is we're saying, I'm going to take some other modules xi, and I'm going to look at their injective co-resolutions. And so it turns out that those will be related to the co-resolutions of the projectives by multiplication by some other upper triangular matrix. But so if we can arrange to have some modules like this, this basically, so existence of Coxeter witnesses would explain the results of the combinatorial results that I mentioned from the paper with Defant. And so let's look at an example. So here was my example of this pentagonal lattice, which was sort of bad, if you like. So it turns out, though, that it is semidistributive. It is, of course, the lattice of torsion classes of A2, of an A2 quiver, so it is semidistributive. So these results from my paper with Defense do apply, and so we can ask, well, is there some nice collection of modules? And it turns out there is. So that's what we have on this page. All we had to do to get, so what we want, remember, is we want, I always get confused about which one I want to click on. So what we want is to have a bijection from the from my well, we want a bijection from the tops of the Coxeter witnesses. So we're in each case for the Coxeter witnesses, we're looking at xi mod rad xi, and that's supposed to be the simple at I. And so that's so instead of just having all the projectives, we have changed this one here so that we didn't take the projective, which would have been two-dimensional like that. We got rid of the guy here. So we took a certain quotient of that. And now we're looking at the final terms in the injective co-resolutions, and now we're going to have a bijection. So now what we see is that each indecomposable injective shows up as the final term for a different thing. And that is basically saying that if we write down the, if we write down this thing that's no longer the Coxeter matrix, but that's recording the multiplicity of the indecomposable injectives for the co-resolution of the Coxeter witnesses. So that's this phi tilde. Well, this guy can be understood, or this guy does have this property of being upper triangular after a permutation of the rows. So that's basically this permutation property that I had underlined here, right? So we can write it like that, and then the actual Coxeter matrix can be written as some upper triangular matrix times phi tilde. So this part is the phi tilde part from there, and then there's some upper triangular matrix which reflects the fact that we replaced the projective here by something that was the quotient of the projective by some other projective. And then, and so then what we get is that the permutation matrix that appears here really describes row motion. And so okay, that's all well and good. That if we had Coxeter witnesses, this by definition is we're just asking for some modules that satisfy certain conditions. If we had them, it's kind of easy to see that they would explain these results. So do we have them? And the answer is yes. So theorem the modules so the interval modules xi with top at I and socle at I join row of I are Coxeter witnesses. So these modules have this good property, and therefore by looking at their injective resolutions, we can see, we can sort of explain representation theoretically these results that we'd previously obtained combinatorially. And that's what I wanted to tell you about. So thank you very much.
Thank you very much. It was very interesting. Do you have questions from the audience?
I do. Actually, about this last part, it looks very, very much as if you, I mean, because you have a quiver which is oriented, you have no cycles and so on. These algebras are quasi-hereditary, aren't they?
Ha, yes. Okay, so I was also super interested in that question.
I mean, this matrix that you need, I mean, I'm thinking of a tilting module and the standard modules associated to that. I mean, given like a linear ordering that your linear extension, sorry, that you're having, this gives you a natural like a quasi-hereditary structure, and this gives you standard modules, and these standard modules have a tilting module associated to that.
Yeah. So yeah,
tilting, you have an inverse matrix, and maybe I was wondering if you have thought about that.
Yeah, so we have definitely started thinking about that. Not everything seems to work quite as well as I would have expected, I guess. Yeah, it doesn't seem. I'm sorry, I'm kind of not remembering all the details of what we did, but what we looked at. But my initially, I was certainly very enthusiastic about the idea that this would have to do with quasi-hereditary structures, and I think actually already for some distributive lattices. So even like even in like the kind of very simple case. Right. So for distributive lattices, you can take the projective modules, but this description that I gave for the Coxeter witnesses is not the same as that. And that, so that description works, and distributive lattices are semi-distributive. You do get Coxeter witnesses, but they don't come from a quasi-hereditary structure.
They're not the standard modules of a given ordering.
Yeah, exactly. So right. Which was yeah, it did come as kind of a surprise and something of a disappointment. Nonetheless, like even okay, so but I mean but it's exactly true. It's completely true for like the Tamari lattice. So it suggests that like for at least some classes of lattices, there is some connection to quasi-hereditary structures. Maybe more, to my mind, more enticingly, it makes me feel like there should be some kind of, weakening of quasi-hereditary structure that should be applicable actually to what we're doing.
Right. Well, there is all this notion of tau exceptional sequences, and there is stratifying systems, which is a generalization of of like exceptional sequence.
Right.
And I have studied this, and this always corresponds to certain orderings of a tau tilting module, for instance.
Okay.
Yeah, I mean, these witnesses seem to, I mean, do you get a nice projective presentation of these witnesses using this description that you have, or not?
I think. I mean, so the projective presentation of the witnesses is related to the first upper triangular matrix.
Right.
And I'm not sure what we know about that. I'm sorry, I kind of forget the details.
Doesn't matter.
There's yeah, yeah, it's I mean, it's like, it's also interesting to think about, like, the positive hereditary setting. It's interesting to think about the co-standard modules. You know, anyway, there's like lots going on. It's not clear to me quite how it all fits together.
Right. Yeah. It's just, I mean, the stratifying systems, essentially what you don't want is a map in one homes in one direction should be 0, and x in the same direction should be 0, and everyone should be rigid, and that's all you ask, right? And
So in what way is it different from exceptional sequence then?
Right, that the exceptional sequences, you want all x to be 0. So if
in one direction,
if your global dimension greater than 1, right?
Mm.
For exceptional sequences, you also need x2, 3, and so on to be 0. And stratifying systems do not ask the higher x to vanish.
Oh, interesting.
Yeah.
Okay.
And whenever you have that, you could show that there is a tau tilting module and a certain ordering on this module that realize this, like having torsion-free parts. So you have the tau tilting module, you order it in such a way that the last guy is exactly the last element in the stratifying system. The one previous to last is actually the co-kernel of the approximation of the last object in the decomposition to the previous one, and so on.
Okay.
I mean, in the same way that you build standard modules, you do the same using certain orderings of tau tilting modules that essentially you ask the orderings are those that allow you to have non-zero co-kernels of approximations. This always exists, and when you have this, you obtain always a stratifying system, and there is a bijection between these two.
Okay.
And yeah, I mean, in particular, some tau tilting modules are tilting, and maybe this is what gives you. I don't know, just conjecture.
Yeah. Okay. That's certainly that's not a direction we had explored, and I will have to look into that and see if it turns out to be relevant.
Yeah, and I have another question, which maybe is not makes no sense in bigger examples, but the two objects that you took were, I mean, the two lattices that you took is, on the one hand side, the torsion classes of A2, and the other one is the dig path, right?
Yeah.
Are the dig paths always distributive or not necessarily?
Yeah, they're always distributive.
Right. So there is this Chapoton conjecture, is it, that there? Could you use your results to at least, I don't know if prove it, but at least try to disprove this conjecture in a way, or?
Whew. I mean, well, so this is related to what I sort of like alluded to, but only very briefly. That I mean, Chapoton conjectures that they're that the
derived equivalent.
Different algebras should be derived equivalent and fractionally Calabi-Yau. And so that's related somehow in my mind to the fact that rowmotion has low all the orbits are small size, and they're at least the least common multiple of the sizes is small.
Right.
But I don't have any precise explanation.
Right. Okay. Okay.
Yeah, I mean, it would be super interesting. You could imagine, if you had, an exceptional sequence or something that would allow you to write down some equivalence to some other, like a different presentation of the triangulated category using some, using perhaps these Coxeter witnesses as something like,
Yeah, it doesn't matter. I mean, it was just
no. I mean, I definitely, I mean, yeah, like this is sort of, I don't know. I feel like you're thinking along lines that also strike me as promising and interesting.
Okay. Well, yeah, thank you very much for the talk. It was very, very interesting.
Oh, well, thank you.
Do we have any more questions? Well, it doesn't seem to be the case, so let's thank you again.
Okay. Well,
bye.
Thank you so much.
Yeah. Bye.